Next we are having a packing in ionic solid. We learn about how the atoms are arranged in a packing. Packing means where we talk about the arrangement of a particle in a given solid. And we just in the previous lectures we did the packing in a solid. That means how the particles are arranged in a particular solid. Now here we are talking about the packing in ionic solid. The ionic solid, about which we know that here we have two different types of the constituent particles. That is the cation and anions. The particles are here cation and anion, while other types of crystalline solid have the same type of particle. If I am saying a molecular solid, all are molecules and all are same type of molecule. If I am saying covalent solid, all particles are atoms of the same type. And if I am saying it is a metallic solid, then all the cations which are present, they are of same type. But here when I'm talking about the packing in solid, when I'm talking about the ionic solid, here the constant particles are cations and anions. Cations which carry the positive charge and the anions which carry negative charge. Now the cations are formed after the loss of electron and the anions are formed after the gain of electron. And generally when an atom loses electrons, the size decreases, while when an atom gains electron, the size increases. So here I can say the cations are smaller in size and the anions are bigger in size. And it has been observed in approximately all the type of ionic solid that the cations and anions which are present, they are of different size. That means cations are smaller in size and anions are bigger in size. So cation size is small and anions are bigger one. Now when we observe in a ionic solid, the arrangement appears like after every cation there is an anion, after every anion there is a cation. It appears like the same way. Like if you are saying a ionic solid, then it will looks like that if there is a cation, after every cation, suppose if there is a cation, then after every cation you will get an anion, then again a cation, then again anion, again cation and again anion. Means the arrangement is something like this. But if it appears like this. But if the particles are going to be, if the particles will be placed like this, then I will say that packing is going to be the worst packing. That is efficiency, that it will not be going to be a more efficient packing. While the ionic solid is considered as the highly efficient packing. That means its packing efficiency is very high. And if the ionic solid packing efficiency is very high, that means the particles are not arranged like this. I said they appears like this, but the arrangement is not like this one. So what happens in case of ionic solid? We have like A type packing, AB type packing, ABC type packing, in which we were having a layers, and in all the packing, the spheres which was present, all the spheres was of same size. So we had learned about this type of the arrangement of the particle, that is a packing in solid. Now if it is an ionic solid, then whatever the particles are there which are forming the packing, that is the spheres which form packing. So these are the spheres which are forming a packing. They all are anions. Means they all carry negative charge. They all are anions. And the particles, that is the cations which we are having, the cations are always smaller in size compared to anions. So what happens, the cations which are there, for forming a efficient packing, it occupy the voids which are present between the anions. So these voids are occupied by the cations, and sometimes all the voids are occupied, sometimes there's only few number of voids are occupied. So how many voids will be occupied by the cation? It totally depends upon the stoichiometric ratio of the cation and anion. So it is decided by the stoichiometric ratio between the cation and anions. So cation can occupy all the voids, or it occupies some void like 1/3, 1/4, or 2/3, or I can say half of void, something like that. So this is the arrangement of ionic solid, I can say, where the anions are, again I am saying that anions are forming a packing and the cations occupies void, because the anions are bigger in size and hence it form packing, and the cations smaller in size, hence they are present in void. And since the cations are occupying void also, so here I can say due to the presence of cation in a void, the packing efficiency becomes, means some vacant spaces are also getting occupied, and that's why I can say the packing efficiency increases. And that's why the ionic solids, because of that such a strong packing, the ionic solid have the high melting point and high boiling point. Okay. Now, here the cations are occupying a void, and we have already learned about 3-4 different types of a void. The one out of which the one is called cubic tetrahedral void. The tetrahedral void which is surrounded by the 4 spheres. It's a void which is surrounded by 4 spheres. Then we have learned about the octahedral void. That is a void which is surrounded by the 6 spheres. So I can say the tetrahedral void, the coordination number is 4, octahedral void coordination number is 6. We have cubic void also, which is surrounded by 8 spheres. And in addition to these 3, we have one more void that is called as trigonal planar void. Trigonal planar void which is surrounded by the 3 spheres. So the coordination number of trigonal planar is 3. For tetrahedral it is 4, for octahedral it is 6, and for cubic void the coordination number is 8. Now the cations occupies the void which is formed during the packing of the ionic solid. Now cations occupy which type of void, whether the cation will occupy trigonal planar void, or it will occupy tetrahedral, or will occupy octahedral, or will occupy cubic void. It totally depends upon the size of a cation. If the cation is a smaller in size, I will say it will occupy a small void. If the cation is a bigger in size, it will occupy the void which is bigger in size. Now how to know which void is a smaller in size and which is a bigger in size? I will simply say that as the coordination number of the void goes on increasing, the size of a void also increases. That means higher the coordination number of the void, larger will be the size of a void. Now in case of this, I can say trigonal planar is having the smallest lowest number of the lowest coordination number, so it is going to be the smallest in size. So trigonal planar is the smallest in size. Then we have the tetrahedral void which is surrounded by 4 spheres, that means coordination number is more. So size of a tetrahedral void is bigger than trigonal. Octahedral void size is bigger than tetrahedral and trigonal, and the cubic void in all the case in this, the cubic void is the biggest in size. So if the cation is a very small in a size which is occupying a void, then it will occupy a trigonal planar. If it is slightly bigger, then it will occupy a tetrahedral void. Still bigger will occupy octahedral void. Still bigger will occupy cubic void. And if it is still bigger, then I will say still it will occupy the cubic void only, but all the particles which are surrounding to the cubic void, they will move slightly away from each other. So this is about the packing. That means which cation will occupy which void, it depends upon its size also. Now we have a rule called as the radius ratio rule. Radius ratio rule for the ionic solid. The radius ratio is nothing but the ratio of the radius of cation to the radius of anion. It's nothing but the radius of the cation to the radius of anion. The cation and anions both are spherical in shape, and being a spherical in shape, its size is decided by the radius of a sphere, that is for cation and anion, plus that is cation and minus that is anion. Now with the help of this radius ratio, at least I can predict that the cation will occupy which void, whether the cation will occupy trigonal planar or tetrahedral void or octahedral or cubic void. It is decided with the help of this radius ratio value. So radius of cation to the radius of anion, r plus upon, here I can say the cations are smaller in size, so its radius is also going to be smaller. Anions are bigger in size, so its radius is also going to be bigger. That means here I can say the denominator is bigger than the numerator, and since the denominator is bigger than numerator, so ultimately the radius ratio value is going to be smaller than 1. That is, I can say that radius ratio value is not greater than 1 except some example. Otherwise the radius ratio is always smaller than 1. Okay, now as I said, with the help of radius ratio value, we can predict that cation occupy which void. For example, suppose I have a particular ionic solid AB, where A is a cation and the B is an anion. I calculated its radius ratio. I just calculated the radius of cation to the radius of anion, that is B minus, and I got a value as a 0.287. I got this value, and this value of radius ratio predict that the cation will occupy tetrahedral void. Why I said tetrahedral void? Because this value falls into the range of 0.225 to 0.414, and this range is assigned for the tetrahedral void. That means all the radius ratio, if the radius ratio value falls in this range, that means the cation will occupy tetrahedral void. So here this 0.287 falls to the same range, and that's why I'm saying that this solid AB, in solid AB, the cation A will occupy tetrahedral void. Similarly, like a tetrahedral void, we have the range for radius ratio range for all the other voids also. So now let's see the radius ratio range for the different voids. So we have radius ratio, that is r plus upon r minus is a ratio of the radius of cation to the radius of anion. The value will tells us about the void which the cation is occupying. Then coordination number of cation, and finally we will have example. Radius ratio. The first range is 0.155 to 0.225. Means for any particular solid, if the radius ratio, the value of a radius ratio falls into this range, then I will say that particular solid will occupy trigonal void. It will occupy trigonal void. So not trigonal planar, it's a trigonal void. Okay, if the value, the other range is 0.225 to 0.414, if the value falls to this range, then I will say that it occupies tetrahedral void. If the range is 0.414 to 0.732, then it is octahedral void. And if the value is greater than 0.732, means I can say 0.732 to 1, then it occupies cubic void. Then we have the coordination number. So finally here I got the radius ratio range for all the different types of void. Then we have coordination number of cations. Coordination number of cations. Suppose if there is a trigonal planar geometry, if there is a trigonal void, that is a void which is surrounded by the three sphere, 1, 2, and this is the third sphere. This is the trigonal void, and suppose there is a cation which is present in this. This is the cation which is present in a trigonal void. So I just wanted to know the coordination number of cation. So the cation which is present here, the coordination number means the total number of touching spheres. So this cation is touched by how many sphere? I can say 3 sphere. So here, and if it is a tetrahedral, then tetrahedral there will be one more just above these 3. There will be a one more sphere. That is, so in this case the tetrahedral, the coordination number, tetrahedral void is surrounded by the 4 spheres. So when a small cation is present in a tetrahedral void, then that tetrahedral void is also surrounded by the 4 sphere. That means if the cation is present in a tetrahedral void, it will touches by the 4 sphere, so its a coordination number will be 4. If the cation is present in a this trigonal void, then it will be in a contact with the 3 spheres, so its coordination number will be 3. If the cation is present in a cubic void, then the sphere will be surrounded by 8 sphere, and hence its a coordination number is going to be 8. So coordination number of the cation trigonal planar, as I said here, it is 3. Tetrahedral it is 4. Octahedral surrounded by 6 sphere, so the cation will also surrounded by 6 sphere only. And cubic, it will be surrounded by 8 sphere. Let's see certain example for this. For the first one, we have B2O3. For tetrahedral whose coordination number is 4, we have the zinc sulfide. In addition to zinc sulfide, we have CuCl, CuBr, CuI, etc. Then this octahedral, we coordination number is 6. So example is CsCl, the cesium chloride. In addition to this, we have CsBr, NH4Br, etc. And for this octahedral void, the examples is NaCl, NaBr. And for cubic void, we have the example like CsCl, CsBr, NH4Br, etc. From this table is a very, very important for us from the MCQ's point of view, that is entrance exam point of view. And for all these examples are very important. Means from this B203 is a very important, ZNS is a very important example, NaCl and CsCl, because many time in exam they ask the question on this. Other examples are not too important, but you should know that if it is a zinc sulfide, then the zinc can occupy which void. NaCl comes under which category, that is tetrahedral, octahedral or cubic, as well as for the CsCl. So these are the certain important example. So here I can say that in case of CsCl, the cesium ion, the cation is a cesium ion which occupies the cubic void. In NaCl, Na plus occupy octahedral, and similarly in zinc sulfide, the zinc ion occupies tetrahedral void. So this is the radius ratio range, and this is the coordination number of the cation, and these are some examples. And as I said, these examples are very, very important one. So that ultimately the radius ratio help us to decide the stability of the ionic solid, as well as it tells us about with the help of this we can predict that cation occupies which type of voids in a given particular solid.